Welcome. Now, this is red bag. Pay attention now. We will go to other side of programming to discover machinery of the language, to unlock power of the language. This is language tree. Tree makes subtrees within. We are saying branches, but we need to start thinking in terms of subtree. It makes subtrees. So here main trunk of the tree is divided into sub-trees. I'm Georgian, and this is Georgian subtree. And in Georgian, heaven sounds like samotche, and words convey meaning, and in Georgian words samotche conveys meaning like 3, 4, 3, and on the slide we see 3 subtrees, and where is the fourth? And the fourth are roots, and wisdom are in roots. So let's go to the roots. Let's speak about roots. So tree and language has really similar in terms of roots. We can say the most abstract definition to create new word. Humans, we developed like this. We write this word. In this case, we write abstract symbol S. Then from new line, we don't put dot here. From new line, we write one or more name-defining sentence. Name-defining sentence. For example, we put S. It can be B dot. It can be S and A dot. It can be S and then T dot. Here we see so-called left recursion, when name defining paragraph start with the name it defines. So we need to start thinking of those paragraphs as growing paragraphs. It grows S. Whatever S is at current moment, it will add A. After it will add A, dot comes, right? So S becomes with A. Then on the second try, it can add another A. In the nature, tree grows cycle by cycle. So on the second cycle, it can add A and so on. This is most abstract definition. In computing, we don't using those definitions. We don't in every day. We don't using power of this because we don't have generic algorithm. Let's go there. To process roots. In other words, to process language. We don't have general algorithm, so we don't have language processing unit. What we have is a CPU. CPU, we can think about CPU. Let's discuss machinery of CPU as a book. So it is a book. We can think about it like dictionary. It gives us, it's printed in source language, in the language of transistors and the laws of current, and it gives us new actionable numbers which we can write on the paper inside of computer memory. Let's call paper, and we need to use these instructions here, architecture definitions, how to fill text members. All types of writing, left, right, from top to bottom, symbolic, all types of writings we have, we can use this abstraction. All writings use text members, and then we fill those text members differently. In computer case, we fill with numbers. In languages cases, we fill with words. In symbolic languages cases, we fill with symbols, and so on. So it's a book. It's a book like normal book. We can see here this writing, and and then this book is enumerated like chapters. So in CPU we do same thing. We are enumerating circuits, and additionally, to create a sublanguage, we need to define most abstract action, and this most abstract action is an action which we will use from every other page, because when time comes we need to go there, so it redirects, use sentence to redirect to another, to connect everything together. So let's see sentence. Here is the memory. In memory, red squares means text members, and little squares are just cells. Cells are filled with values, with numbers, and text, each first cell of text member means the actionable number. So CPU additionally has execution context. Think about it like we have eyes, right? And our eyes always is in focus on concrete word when we process and we read text. So CPU also has special program counter focus, which is always on current text member. So when CPU fetch, decode, execute loop turns, it will move focus to the next text member. It will read information there, find that that's 0. It will use book. It is the book. It will use book and take move circuit there, move execution flow there. So now time is to this circuit to execute. When this circuit will execute, it will finish executing. It will return to fetch, decode, execute loop. That's how all is connected together. That's really simple, moving from left to right through fetch, decode, execute loop. Most abstract actions. Now, in the CPU gives us the language. So current language is a language of instruction set, right? We can create sub-languages, and in there we can have as many books as we wish. We need to find a way how to compose those books. Let's go there. So this is slide summarize all of our technology, which is defined in mathematics and which is defined by hardware in the source language of our universe, all together. Here is Turing machine in center. All of those technologies do not give us straight path to process roots, to define things in most abstract definitions, to use most abstract definitions to create most composable, most powerful self-learning things, to be able that everyone can be able to write simple text, right? So everyone knows how to write text members. So anyone can become programmer. So let's go there. Actually, we have several methodologies how to process these types of writing routing system, but it without context. In other cases, we need to modify routing system to eliminate left recursion. Today, it's a problem. Let's solve this problem. From A to B, there is shortest path. There is shortest path. We don't need many algorithms. We need shortest, right? So if we look at this straight line from the left side and we turn this, we will see this as a dot, right? So that's the shortest path is the dot. We need to go into dot. We need to think of sentence as a thing in which we can go into, as a tunnel. Here is the Georgian alphabet. It's 5th century BC, if I don't mistaken. And in center here is a beautiful cross, right? And I want to show you similarities. Here is me sitting in front of my computer and looking in this mandala. It's instruction for me how to see things inside sentence. I see here one sentence in this dimension. Although I'm looking through the sentence, I see several protocols, different colors, right? We can observe all those things. And text members, like we can see 3 text members. So we developed this protocol in Georgian language in mind and Georgian grammar in mind. We developed this protocol based on Georgian grammar and also based on this phrase, Aradani Archevani. It was inspiration for me. Aradani Archevani phrase, we can translate it as not and or is a choice. It means not and or. In the logic, mathematics, all you need really not and or to make any logical expression. So not and or is a choice, yet it is. So imagine moving in the text members. We can define those junctions as not and or and make composable all text members together. We can have several sentences in one paragraph. Here is the one dot, here is the text member, and that another dot, and here is the closing 0, empty space. We are using to write 2D paper. So Turing machine use tape. We are using paper, 2D paper. It also, of course, it mapped on 1D array, but it mapped with alignment. So we can think about it as 2D. We can move up and down, left to right, and so on. Here is the one sentence zoomed. Why we need so many turns here? It's influenced by Georgian language, and basically in Georgian, sentence can be divided in 4 main parts. For noun, for subject, for object, and so on. We call them it's like this. when I was listening to these videos, there was this phrase, I want to say it in Georgian. კარგად დაიმახსოვრეთ ბავშვებო, ქართულში წინადადება შედგება 4 ძირითადი ნაწილისგან. So, in Georgian, sentence composed from 4 main parts. This means those parts can be presented in the sentences with several text members. So, for example, part which represents subject may be represented with several text members. And also part which represents object may be represented as several members. And those members do not require to be in perfect order. You can put anywhere. There are some syntactic rules which is evident when you write sentence that it's not make any sense. But in most cases, the order does not matter. That's why we need several turns in the sentence. So when we start from yellow, we move into fuchsia. That's time for Quemdebares to show themselves and use memory. We will show what memory means to put their information. Then shemasmeneli, then piktapiri damateba, then iribidama, and so on. And then time to interpret this sentence, to put dot, to calculate something and go to next sentence. This first sentence is 3, 3, 1. So, how to use this protocol as a routing machinery to write descriptions in roots, in most abstract definitions in 2D paper, and how to use those roots, how to apply context. And really, what is context? Because we struggled a lot on this to solve this problem, and lately I saw a video on the YouTube, and I want to thank you whoever did this video. There was a video about quad tree structure, and I saw this structure, and I tried it. I captured the moment that I need to try this. I tried it, and what it is, these two quad tree structure is a memory. So imagine this writing here onto the paper, and one pyramid on top of it, and other pyramid from the bottom of it. In Turing machine we have tape. On the tape is a Turing machine's head, and it moves from left to right. We have paper, and on a paper from both sides there are pyramids. This is memory. When we interpreting routing system and we find symbol and we need to find where this definition start, we will change book of interpretation, start looking for, we will take book of searching, start looking, search, then we will find S, we will go into first sentence, we will change book of interpretation, and while we are doing so, we are saving how to return back, what to try next on those pyramids. So here is the key: how to solve left recursion. We need to think in different terms, in terms of growing. When we are learning these stuffs, right? When we are learning computation theory. In computation theory, we are learning to substitute symbols with productions. There we are calling those things productions, although they are name-defining paragraphs. And I want to underline this fact because in paragraph there can be several sentences. So we need to start thinking in terms of grow and to identify this truth. The sentence has two sides. When we are at dot, we already know something. We already finish it to interpret something, right? Here we are on S. So we know S. We need to place cursor on this time to try all other name defining sentences, which is left recursive, only skipping left recursion. And we will go to the dot, we will do the same. That's how we can solve left recursion. And we are at the beginning of the sentence. We just save another sentence, cursor in time, and we will finish current interpretation, because those definitions can be ambiguous, right? So we need several answers for some questions. And answers we can add to routing system, and the routing system can be symmetric. So in other words, in computing, we have this algorithm, so-called backtracking algorithm, to solve this type of things, right? We don't need backtrack, we need memory, and that's how we can implement memory. And to say how we solve the problem of guaranteed deceiveness, and it's the same as left recursion, it's the same as halting problem. We solved it like we closed system defining language. We are creating sub-language, sub-world, and in sub-world we converted space into time. When we writing things into memory, we can return to memory, means we can return into time. So we managed to conquer time. We converted space into time. In other words, we can say that in our universe, we all are so-called machines, right? We all have choice. We can choose to do same thing every day, and how in case halting problem is solved. We are limited in time. We will halt anyway, sooner or later. So that's how it is done. Let me show the algorithm now. All algorithm you can place on one slide. It's in colors. It's just overview. Here is in colors we are building those Aradani pyramids, and also doing concrete stuff. Well, we are moving in current interpretation time, and we are we are cursoring plans on those pyramids. Here you see fetch, decode, execute loops. We have several of them, and dynamically we are changing to all this process be not without context, but with context. Here it's the main sophisticated part. Here is the steps which we use to climb on those heads, pyramidal heads, for different sites. In other words, to execute plans. Each side is divided with plus in three arrays, in not and or arrays. This is not, this is and, this is or. So there is 4, 8, and each can be divided in 24 different arrays, which through this arrays we guarantee decisiveness. So when system will halt, it will tell you I am halted, and here is my current state. So run me in the big box if you want. Now here is the grammar. Here's the macros to write it on 2D space. Yeah, how to map it on 1D. And we can run this one, S grammar, right? To see how it runs step by step. Here we have debugger. And debugger works like this. On the sides, we are looking inside the Aradani pyramid. This is one pyramid, this is another. Different colors, yellow, red, blue and green for one pyramid, to saving what will come next, and other pyramid to go back, to saving plans how to go back. And we can turn the debugger in full duplex mode to see both pyramids together. So we are on the symbol S. Now book of interpretation is about to go with the roots, find symbol S, immediate value S. So we change book of interpretation. Now it's a book of searching. By the searching book, actionable number 1 means move up just, and actionable number 3 means compare those two things. All those immediate states are kept in those pyramidal structures, and everything is intact. Everything is immutable. So you can return exactly in any moment in time. So this is time machine. So when we are here trying to go into the first name defining sentence, as you can see here on the yellow, we cursor this moment to try next when we finish current interpretation. So we interpreted S as a B, and now we are in dot, right? So we are putting two cursors, right? And continue interpretation. We could putting two cursors, one cursor to check all name defining paragraphs, but those which has left recursion inside, and skip left recursion. Because we know something about this, let's build on top of it. If it has left recursion, we can't know it in advance, because routing system is a really dynamic system. So we finished current interpretation. 5 means print. We printed B, and now we are at 0. And 0 means let's go climb on yellow side of the pyramid. And here is the cursor. And cursor, we just start executing the yellow side of the pyramid, climbing. It will go back from S. We found S earlier, right? We saved this position, and it will try all those name defined paragraphs which has left recursion now. So it will try first. It don't start with left recursion, so it will skip this one. Here is left recursion. It will put A, here is A, B, A, all states, everything, when we return, it will update everything. Now we are at dot. We will do same, we will add cursors. And this is fractal in nature. And that's how it works. And let me say a few things about this paragraph, last paragraph, because it has two name-defined sentences, first one and second one. When we finish this one, there will be time to try additionally. And this kind of expressiveness is the first time we are introducing in computing. And that's how it works. Every time it halts, this is generation now. It will generate in space it allocated everything it can. So every time it halts, and it will telling me that I'm halting, I can't go further. But in parsing mode, it will stop when it needs to stop. If it has enough time, right? So we can try this grammar, AB grammar. This grammar has indirect left recursion. So let's see how it handles indirect left recursion. So here we have A defined in routing. This is all the routing system, right? What is grown in the memory, and in the memory we can add additional two pyramids to produce values there, or anything really we want. So here we try to find A, we found A, so it's B. We are now in dot. Let's try all the left recursions. So we finished interpreting first cycle. We finished first cycle. Let's think in terms how tree grows, natural trees. It grows cycle through cycle. So first cycle, then next cycle. We started here. And now we need to try all the name-defined paragraphs which introduce left recursion. This will not introduce left recursion, so we'll skip this. This maybe introduces left recursion, and we don't know in advance. We can't know in advance. Routing system is a really dynamic system, so we need to dive in. Let's dive in. Now we are diving with different book to seamlessly process to guarantee the seamless. We found in B that this is not introduces left recursion. We are not trying to define same symbol, right? So we're skipping this. Now we found that we are introducing left recursion. So we need to add to base to this part from skipping A, this part, and then this part. We already saved this place in the return pyramid, so we can do this pretty easily. So it's BA. So it's B. It must be O here. BBA, right? Okay. So that's how it's done, right? Let me say three things about this. This is at level of C. We are introducing first time generic algorithm which can process natural, which can be grown to process natural language to compose text, most abstract actions written in natural language to build really efficient and scalable systems. self-conscious systems. We can try expression grammar. Here is a little bit deeper memory allocated, deeper space allocated to him, time. So here is the expression grammar. As you can see, it's pretty ambiguous grammar. So let's try from console. Here is, those are all mathematical expressions, right? This is how it works. So thank you very much. Any feedback will be appreciated. Thank you.